Hello all, I am Shatabdi Acharya from Vedang Institute of Technology. In our earlier videos, we were dealing about inductive effect. So, continuing our lectures further on the effects of inorganic compounds, we will move on taking up hyperconjugation. So, before moving on to the topic, first let us understand what is hyperconjugation. First of all, you might be clear on the word conjugation. What do you mean by conjugation? It means alternate single bond and double bonds, right? Now, why is this effect so significant? Like, why are we studying even conjugation? See, suppose I'm having a carbon chain wherein carbon atoms are connected by single bond followed by a double bond, then single bond and double bond. Basically, a system of alternate single bond and double bond, a conjugated system. In that case, what happens? How this double bond is formed? Basically, the p orbitals of these two carbon atoms, they overlap in a sidewise fashion, in a sidewise manner to form this pi bonds, right? Pi bonds are formed above and below the plane. So, the same situation might have happened with these two carbons also. Now, if I look at this carbon, which is singly bonded to the other carbon, carbon number 2, let me number this carbon for you, 1, 2, 3, 4 and 5. Now, if I see carbon number 1, in carbon number 1, its p orbital is vacant. Okay, its p orbital is not like involved in a sidewise overlapping fashion with the carbon number 2. That means it still has the scope of overlapping with that. When such a system arises, what happens? These two pi bonds, they have a tendency to influence this vacant p orbital, and similarly these two carbon atoms bonded in a pi bond fashion, they have the tendency to influence the other two non-bonded p orbitals. As a result of which, what happens? The pi bond now is not remaining localized in between these two carbon atoms, rather it is spread out in the entire chain. Now this was the case with pi bonds, but can only pi bond have the tendency to show this conjugation, or it can be extended to sigma bond also? This can be clarified if you go deeper into this lecture. So, what we understood of the word conjugation, that means it is a system of alternate single bond and double bond. Okay. Now, in conjugation, the electrons move from one p orbital to the other, which are aligned in a parallel fashion. Fair enough. We had seen it in the previous example I was showing you. The p orbitals which were present parallel to each other, they were overlapping in a sidewise manner in order to form a pi bond system. Now, is it possible for the electron to jump from p orbital to sp3 orbital? Although sp3 orbital is in a trigonal plane or a tetrahedral fashion, okay, it is not parallel to the empty p orbital, but is it still possible for the p orbital to influence an sp3 orbitals? Obviously yes. This system of conjugation is called hyperconjugation. It is not normal, it is not the system of traditional parallel system of p orbitals, where the p orbitals were parallel to each other and they overlapped among themselves to form a pi orbital system. Here what happens? One p orbital influences an sp3 hybridized orbital, and that system is known as a hyperconjugated system. Okay, that is called as a hyperconjugation. This type of conjugation is not normal, it is extraordinary, hence the name hyperconjugation. It is sometimes called as no bond resonance. Now, why it is called so? Let's see. We have seen inductive effect. What do you mean by inductive effect? It is the bond polarization effect when carbon is attached to a group which might be more or less electronegative than carbon atom. As a result, if carbon atom is attached to a group which is highly electronegative or more electronegative than carbon, then what happens? That particular group withdraws electron density from the carbon atom, acquires a negative charge on itself, and the carbon atom from which the electrons were withdrawn, that carbon atom basically attains a positive charge, right? So, what we have found is alkyl groups normally show plus psi effect. That means alkyl groups have a electron releasing tendency, right? which we have studied that in inductive effect. But two other person, Baker and Nathan, they found that in along with inductive effect, there is another reason for these alkyl groups to donate electrons. They can donate electrons first by inductive effect also. Apart from inductive effect, there is also another effect which strengthens the electron donating capacity of these alkyl groups. And we have known the order for plus I effect group is methyl group, then 1 degree, 2 degree, greater than 3 degree. Maximum electron donating effect is shown by a 3 degree carbon or 3 degree alkyl group, because the 3 degree carbon is surrounded by 3 alkyl groups, and alkyl groups or 3 methyl groups, here for example it is surrounded by 3 methyl groups. Now it has the tendency to donate greater electron densities. Now apart from inductive effect, there is also another effect which strengthens the plus I effect, or which strengthens the electron donating capacity of the alkyl groups. Now what is that? When a carbon hydrogen sigma bond is in conjugation, the sigma electrons of this bond enter into conjugation. Basically, they extend their conjugation. Normally, sigma bonds are strongly bonded. They form by head-on overlapping. But when this sigma bond is a part of a conjugated system, what happens? They have a tendency to extend their electrons into that conjugated system. Okay. This term, it is not normal, and hence it is called as hyperconjugation. Okay. Something extraordinary to conjugation, hence the word hyperconjugation. The contributing structures involving sigma electrons do not show any covalent bond. Basically what happens, the carbon hydrogen bond which was there, initially, what happens? This was the sigma bond, right? Now this sigma bond enters into conjugation, and ultimately what will happen? Carbon has a tendency to form 4 bonds. Now if one of its bond is entering into conjugation, then some other bond has to break. So if these electrons are going into conjugated system, then this bond between carbon and hydrogen has to break, as a result of which what we observe is carbon donates its electron at putting its sigma bond with hydrogen at stake. Okay, so we observe that for a partial moment there is no bond between carbon and hydrogen. That's why we have used the term in the previous slides. It is called no bond resonance. That means resonance is, you will understand later, resonance is basically the delocalization of pi electrons. But here what is happening? The delocalization of a sigma electron is happening, as a result of which sigma bond is the primary bond. It is the first bond that is formed by any two compounds. So if this sigma bond is going into in participating in the resonance, then what happens? It definitely has to break that bond with the other atom. Now there is a for a partial moment there a situation arises where there is no sigma bond between carbon and hydrogen. Therefore this condition is called as no bond resonance, and it is termed as hyperconjugation. Okay, therefore it is called as no bond resonance. Okay, no bond resonance, and this condition, hyperconjugation, is this condition is called as hyperconjugation. So hyperconjugation can alternatively be called as no bond resonance, right? Now see here what happens. This is an explanation. There was a sigma bond between carbon and hydrogen. This basically signifies a sigma bond between carbon and hydrogen. And suppose this is an alkene system. Okay, this is a pi bond. Now what happens? When this pi bond is shifting onto this carbon, then this becomes empty. These orbitals become empty. As a result of which what happens? This electron density present in its adjacent carbon is donated to that empty carbon in order to extend its conjugation, in order to stabilize the unavailability of electrons on the second carbon, on this carbon atom. Okay. So basically when this pi bond breaks, the donation of this electron makes this carbon atom stable. Okay. Similarly, it is showing the same situation. You can observe it here properly. What happens? This bond, this sigma bond is breaking when when this pi bond between these two carbon atoms, they are being broken down, as a result of which there is a vacant orbital in this happening in the second carbon. In order to balance this one, the carbon hydrogen bond breaks itself, as a result of which there is development of a pi bond between these two carbon atoms, and what we observe is there is no bond between this carbon and hydrogen. But is it that situation that this bond will break and this will get released out as a proton? No. What happens? While this process is occurring, the hydrogen, the proton itself is staying in the vicinity of that carbon atom, because what I said is this is hyperconjugation. That means it is also a case of resonance. It is basically happening that there is transfer of electron densities from atom to atom, but as a whole the electron density is spread out on this entire carbon chain. Now that electron density, obviously electron density in itself means it is a negative charge density. So this negative charge density does not allow this hydrogen atom to move out as a proton, as a result of which if a base comes, then we cannot say that the base will extract this proton. No, it's not possible. This proton is still intact with the carbon system. It is a part of that system. Okay, basically what is happening, there is just shifting of charges from one atom to another. Next is, what are the requirements for hydrogen hyperconjugation? The primary requirement is presence of alpha hydrogen or a lone pair of atom. Now what do you mean by alpha hydrogen? Suppose we were studying the system of alkenes, right? So if I am saying this is a system of alkene, obviously hydrogen is there. Even if I am not writing, hydrogen is by default present. So if I am saying this is a system of alkene and these are two doubly bonded carbon atoms, this is my functional group here. Now apart from this, the carbon atom directly attached to this functional group will be called my alpha carbon. Okay, if this is my system, this is my functional group, then the carbon atom directly attached to this functional group is called my alpha carbon. Next one will be beta carbon, gamma, delta, and so on. Now the hydrogens attached to this carbon atom are called as alpha hydrogen. So the primary requirement for the existence or the sustenance of hyperconjugation is the presence of alpha hydrogen. There must be an alpha carbon hydrogen group or a lone pair on an atom adjacent to the sp2 hybridized carbon. sp2 means the one where one p orbital is still vacant, the one where one p orbital is available for taking up the electron density from the adjacent carbon atom. Okay, so there must be a sp2 hybridized carbon or the atoms like nitrogen, oxygen, etc. Example of this hyperconjugated system is alkene, alkyl carbocations, alkyl free radicals, nitro compounds. These are certain examples, or these are certain systems where there is a chance of observation of hyperconjugation. Now due to the presence of hydrogen on the alpha carbon, which is next to the multiple bond, or which is next to that carbon atom which will be in requirement of an electron, the displacement of s electrons towards the multiple bond takes place, which causes the polarization of the multiple bond. Obviously, as the bond is breaking down, it will break into a positive and negatively charged system. Okay, so if I am saying if this carbon atom is there and hydrogen is attached to it, if this is moving here, then obviously this will attain a positive charge and this carbon will attain a slightly or a partial negative charges, right? So due to hyperconjugation, the system of polarization also arises. The concept of dipole moment is also related to hyperconjugation. Okay. Next is applications of hyperconjugation. Now, understanding hyperconjugation was important, but in order to understand the application of hyperconjugation, we need to need to have a root concept of what is hyperconjugation, and applications are way more important than that. By application, we will be able to answer a lot of questions in organic chemistry. Now, what are those? We will take up one by one. The first is stability of alkenes. So what we found is, normally a question might come, suppose this is an alkene and this is another alkene. This is 1, this is 2. Now somebody might ask, why is 2 more stable? Why is 2 a more stable alkene than the first one? Basically, basically what we observed is, in the second case, what we have, to a carbon atom there is a alkyl group attached, but in the first case what has happened is, to both the carbon atoms only hydrogen atoms are associated. So this stability of this alkene can be explained by the concept of hyperconjugation. As a general rule, greater the number of alkyl groups contained on the double bond, greater is the stability of alkene, because with the increase in alkyl group, there will be increase in number of hydrogen atoms. If number of hydrogen atoms will be increasing, then the chances of hyperconjugation will be more. And we have learnt hyperconjugation means the ability of the carbon hydrogen sigma bond to donate its electron density to the other carbon. So alkene is basically an electron rich system. So if there are groups nearby it which are ready to compensate this electron density, if at all it loses at any case by any chance, they will basically contribute to its stability. So increase in the number of alkyl groups increases the stability of alkene. Therefore 2-butene is more stable than 1-butene. This is because in 2-butene there are 6 hydrogens involved in hyperconjugation, whereas there are only 2 hydrogens involved in case of 1-butene. Hence the contributing structures in 2-butene is more and is more stable. Now if we try to draw the structure of 1-butene and 2-butene, I have drawn it here. This is 1-butene and this one is 2-butene. So if I compare this, then the number of contributing structures, that means the number of alpha hydrogens, are more in the second case, while there are only no alpha carbons here in the first case. Therefore the stability of one is lesser than that of the second case. Now if I see this, as I increase the number of alkyl groups, what happens? The stability gradually increases. Okay. The second is stability of carbocations. What are carbocations? Carbocations are the species which are devoid of electrons, where the electron density is less, or which are positively charged carbon atoms. Now if I see ethyl carbocation is more stable than methyl carbocation. Suppose this is a question you have to answer, which is why ethyl carbocation is more stable than methyl carbocation. Now if you look at the structure, this is CH3, CH2 plus. Now here this carbon atom is attached to 3 hydrogen atoms. That means this is the alpha carbon, this is our carbon to be focused on, and the next carbon to that is obviously our alpha carbon. So in our alpha carbon there are 3 hydrogen atoms. That means there are 3 alpha hydrogens, and each alpha hydrogen has a tendency to donate electron density to the carbocation, as a result of which the 3 contributing structures are possible in the second case, or which is the ethyl carbocation. But in case of methyl carbocation, there are no alpha carbons or alpha hydrogen, as a result of which the number of contributing structures are 0 for this. Now this presence of this alkyl group attached to this carbon atom accounts for or results in the contribution of increase in the stability of the carbocation. Okay. This is because the sigma electrons of the alpha carbon hydrogen in the ethyl group are delocalized into the empty p orbital of the positively charged carbon center, and thus by giving rise to no bond resonance structures. But hyperconjugation is not possible in case of methyl carbocation, and hence it is less stable. Okay. The next is stability of free radical. Now what are free radicals? I have said if there is a if there are 2 carbon atoms bonded by a single bond, then there are 2 possibilities. Like if a carbon is bonded to any other group by a single bond, then there are 2 possibilities. One is apart, like the carbon and the other group, one of them can emerge out stronger and can pull the electron towards itself, as a result of which electron shared between them to itself, as a result of which what will happen, there might be a case, suppose carbon is coming out stronger, then carbon will take up both the electrons, will pull both the electrons towards itself, as a result of which what will happen, it will acquire a slightly negative charge on itself, and the group that is leaving the carbon will acquire a positive charge. Now if I say the group attached to carbon is weaker, comparatively weaker, then what will happen, stronger, then what will happen, that group will pull or take up the electrons from the carbon atom. As a result, carbon will have a positive charge on itself. Now, if the carbon is having a positive charge on itself, it is called as a carbocation, and if the carbon is having a negative charge on itself, it is called a carbanion. Now, the second case is if the carbon atom and the group are of equal strength. The group attached to the carbon, they are of equal strength. As a result of which what will happen? They both will be pulling the electron, both the electrons shared between them towards themselves. As a result, nobody will come out stronger or weaker. Hence, the bond will break homolytically and both the electrons shared between them will be taken up one by each carbon atom. As a result of which, there will be presence of the formation of free radicals. Okay, so free radicals are electron deficient neutral species. Carbocation was electron deficient positive species or positively charged species, but free radical is a electron deficient negative species. The stability of free radical is influenced again by hyperconjugation. The same reason follows, the one we have studied for carbocation, the same follows for free radicals also, because both of them are electron deficient species only. So, the stability of free radical is influenced by hyperconjugation, just as in case of carbonium ions. One of the two sigma electrons of the alpha carbon can be delocalized into the p orbital of carbon containing an odd electron, which is electron deficient. Due to hyperconjugation, the stability of free radical also follows the same order as that of carbonium. Carbonium means carbocation only, okay. Carbonium, which is methyl, which is less than primary free radical, then which is less than secondary free radical, and the highest among them is tertiary free radical, because the number of contributing structures are greater in case of tertiary. Okay. Now, the next application is reactivity and orientation of electrophilic substitution on benzene ring. Now, if I say benzene ring, so how will it look? This is the benzene ring. Standalone, this benzene ring is very stable, right? But if there is introduction of any group, for example, let me say a alkyl group. Now, this group has a tendency to donate electrons. When this will donate electrons, the equivalent structure for benzene ring is this. Now, if suppose this carbon atom is donating its electron, this carbon atom will donate its electron like this, for example. If I say the 3 hydrogen atoms are present and they donate electrons to the benzene ring, how will they do that? This bond will shift here, this will shift here. Simultaneously, this chain will continue, the resonance will continue. As a result of which what will happen? There will be a negative charge on the ortho and para position. There will be negative charge development on ortho and para. Now, question might be arising, what is ortho and para position? Okay, see, if I am saying a normal benzene, okay, with no groups attached to it, in this case, you cannot assign any ortho para meta. There are 3 positions on the benzene ring, okay, which is ortho, meta as well as para. Now, this has no ortho meta para because all the positions are equivalent as there are no substituent on the benzene ring. But once the substituent is introduced, for example, I have introduced a methyl group in this case, then the carbon atoms just adjacent to this group are called as orthocarbons, ortho position. This is suppose 1, this is 2, 3, 4, 5 and 6. Now the 1, 2 and 1, 6, these are called ortho positions. Okay, I'm taking the reference of the group attached to it. So the 1, 2 and the 1, 6 are the ortho positions. The 1, 3 and the 1, 5, 1, 3, 1, 5 These are the meta position. It is the ortho, this is the meta position, and 1 4 is the para position. So there are 2 ortho positions, 2 meta positions and 2 para positions. Now if I shift this electron density on the benzene ring, what I will observe is there is development of a negative charge in the ortho as well as para position. So what will happen? If there is, I have said you what is a electrophilic group, which is a nucleophilic group. Nucleophilic groups are nucleus loving, that means those groups in itself are negatively charged. Electrophilic groups are electron loving, that means those groups in itself are electron positive, positively charged groups. So what will happen? If there is development of negative charge density on the carbon atom, on the ortho and para carbon, then obviously if there is an incoming electrophile, then this group, CH3 group, will direct that group or order that group to take up ortho and para positions. So as a result of which what happen? They will increase the reactivity of the benzene ring, because standalone benzene is very unreactive, because it is a highly stable structure and stability is inversely proportional to reactivity. So what will happen? If there is a methyl group which is an electron donating group, then what will happen? They will increase the electron dense or reactivity of the benzene ring, and orientation means they will direct the incoming electrophile to the ortho as well as para position. Now this, if benzene and a CH3 group is attached to it, this compound is called as a toluene. In case of toluene, the reactivity of the ring towards electrophilic substitution increases, and the substitution is directed at ortho and para positions to the methyl group. This can be explained mainly by hyperconjugative effect. The methyl group releases electrons towards the benzene ring, partly due to inductive and mainly due to hyperconjugation. Okay, so for now we have seen inductive and hyperconjugation used a lot of times, right? Now there might be a question, if both inductive and hyperconjugation are operating simultaneously, then which one will be stronger? So always remember, hyperconjugation is very strong effect than inductive effect. If there is any competition between hyperconjugation and inductive effect, then hyperconjugation will dominate. Now see the next question, we have very interesting question. Suppose you are given a question to benzene ring, one tertiary butyl group is attached and one methyl group is attached. Now in case of HNO3 and H2SO4, we generate a nucleophile which is NO2 plus. Okay, in this nitrating mixture we have electrophile generated which is nitronium ion, which is NO2 plus. Now the question arises, if I look at this group, then this one will be ortho to it, this one will be the ortho position, and obviously the para position is already blocked, right? The para position has no chance of accommodating the NO2 plus. The only positions left are this, ortho to this. Now the ortho to tertiary butyl will be meta to methyl. Now to meta, for example, for methyl, the ortho positions are these two, which are meta to this nitronium, the tertiary butyl group. Now the question arises, to which carbon the nitronium ion, NO2 plus ion, will go? Obviously, if I look at this, the carbon atom has no alpha hydrogen. Obviously, there are methyl groups, there will be inductive effect, but no direct hyperconjugation effect, right? This group is showing a strong inductive effect. Now, here is a case of competition between hyperconjugation and inductive effect. Here both the effects are operating, but they are opposite to each other, they are antagonistic to each other. So in that case, what I have said, hyperconjugation will dominate, as a result of which we will see the directive influence of methyl group primarily. That is, the methyl group will influence the incoming nitronium group primarily as compared to the tertiary butyl group. As a result of which the incoming group will take place either this position or take the place of either this or this. Both are ortho to methyl. So we have chosen this as our suitable position for the attack of or the orientation of the nitronium ion. Right. So these are some of the concepts related to hyperconjugation. I hope I am clear to you. In the next lectures, we will take up the further effects like resonance and all. Thank you. Thank you so much for this video.